Hello, how are you?
I'm fine.
Hello.
Yes, I'm trying to share. Let me just see. Hope you are fine.
Yes.
It's okay. Oh, okay. I was sharing a wrong thing. Can you see it?
Yes.
But I lost it. I don't know why. Let me again share. I can't see it from my end. Yeah, there it is now. So I want us to look at again how to find inverses, this time using the Euler theorem. So that's what I want us to look at today. The other time we looked at how to compute inverses using Fermat's little theorem. And when we met on Thursday, I discovered that majority of you had grasped the concept very well. Those who were present, I was able to see that they have a good grasp of that concept. What I don't know is those who are not present, but those who are present, I saw they had a good grasp. Now, we also looked at the Euler theorem, generally, what it states and how to use it to find the remainder. That is last time. But today I want us to use it to just let me just again look at the Euler theorem, just a statement, and emphasize one thing. Then we proceed to finding inverse using Euler theorem. This is the statement of the Euler theorem. It says that if m is an integer and r is another integer which is relatively prime to m, then r raised to phi of m is 1 mod m. This is what the statement. So what I just wanted to emphasize is that Euler's theorem is only used when r is relatively prime to m. So even the examples we'll be looking at, this condition must be looked at. This condition we must be looked at. And I think when we were looking at it the same Thursday, Alex came up with another condition which I saw was also correct, but I've forgotten what it was. Another condition when we were trying to solve, in the process of solving, another condition emerged. So I've forgotten what it was, but this is the non-conditions. I think that one was about factoring. We were trying to factor, and at some point, it was not easy to factor. And I think there was another condition. But now the condition I'm emphasizing is that R must be, that A must be relatively prime to M for us to use the Euler theorem. Now, so I want us to go straight to how to use it to get inverse. And I began by showing from that statement how to arrive at the inverse, because the statement was that R raised to phi of M was congruent, is congruent to 1 mod M. This was the statement of Euler theorem. Now, to get the inverse, we multiply by the inverse of R. I want the inverse of R. So that means I multiply both sides by the inverse of R. So on the left side, multiplying by the inverse of R, this is what we get. phi of m is congruent to, on the right side, we'll have that because I'm multiplying by the inverse on both sides. Now, so that means the inverse is already here. The inverse is already here. That means the inverse of R, therefore, from what I'm saying, is equals to this. And what is this? We can use the law of indices. On the left side, what we have is R raised to phi of m minus 1. You can also add there mod m. That means for you to get the inverse of any number which is relatively prime to m, for you to get the inverse of any number which is relatively prime to m, then what you need to do, first of all, find phi of m. Then subtract 1 from this, and then raise that number to this power, phi of m minus 1. Mod, you reduce it, mod m. So that's how we'll be doing to find inverses. That's how we'll be doing inverses. I think after this Euler theorem of finding the inverse, then I need now to look what, tomorrow we can look at how to factor numbers using algorithms. I think I look at 1 or 2 algorithms tomorrow, how to factor huge prime numbers. We had not looked at that. Then after looking at that, how to factor huge prime numbers, we shall now proceed to again revise RSA, and then attack it by factoring. You remember when we were looking at the RSA, we said that we can attack this by factoring. The only way you need to do, if you're given a prime product of 2 prime numbers, and we call it n, the easiest way to do is to factor this. So tomorrow we'll be looking at how to factor this number. And we'll look at several algorithms. And then after that, I'll ask that you implement those algorithms. When we meet on Thursday, we try to do it now again live so that people can have a few people in a groups trying to send communication to each other. For instance, one chooses 2 prime numbers unknown to us. Then some of us now come and break so that we can discover the message the two are conversing. So we'll try that on Thursday, but tomorrow first of all we look at how to factor these numbers if they are given to us, huge numbers. So we'll look at several algorithms. Then we do it practically. Then on Thursday when we meet, we try to, a few people can have one person and another one coming up with the keys. And then some of us just sitting somewhere. Then when the public key is announced, we can also know what it is. And then when the ciphertext moves to the other end, we can know what it is. Then we try to crack. So that we shall be doing that practically. But before that, let's look at Euler's theorem and see how to find the inverse. And these inverses, we'll be using them in that cracking also. Now, I want the inverse of 12 mod 19. I begin by checking whether this number and this are relatively prime. And we can see that for sure they are relatively prime. And since they are relatively prime, what does Euler say about the inverse of 12? Euler says that the inverse of 12 is 12 raised to phi of 19 minus 1 mod 19. This is what Euler says from this formula here. What is phi of 19? We looked at this, or we revised this on Thursday. Phi of 19 is a prime number, so it will just be 18. It will just be 18. So what we therefore say is that the inverse of 12 is in fact 12 raised to 19 minus, no, 12 raised to 18 minus 1, which is 17. 18 minus 1 mod 19. Now, once you already have the inverse, actually. This is the inverse. The only thing you need to do is to now use the fast powering algorithm to find out what number is this, 12 raised to 17. That is the only thing we're supposed to do. To use the fast powering algorithm to tell what number this one is. Now, so let's just go straight to the fast powering algorithm. Of course, we already know what the inverse is. We already know that the inverse of 12 is 12 raised to 17. But what is 12 raised to 17? We use fast powering algorithm. 12 raised to 1 is just 12. Then you square this line to get this line. Just open my calculator as you open yours so that we can move together. We are squaring that line, which is 12. Raised to 1 is 12. So in fact, when I raise this to 2, I'll have that 2. So I have no problem with the left side. The only side I want to look at is the right side. The left side, I have no problem. Just raising to 2. What the power that I have, I raise to 2. It's the same as doubling that power. Doubling the power on the left side. But now on the right side, we square. That's 12 times 12, which is 144. Our divisor is 19. So 144 divided by 19 goes there 7 times. Goes there 7 times. The remainder is 11. The remainder is 11. Now let's square this part again. Let's square this to get the next. Let's square this part to get the next. So when you square this, you get 12 raised to 4. When you square this, you get 12 raised to 4. And when you square 11, you get 121. Then divided by 19, goes there 6 times, and note the remainder. The remainder is what we write here, is 7. Now square this part, and when you square that part, you have 12 raised to 8. 12 raised to 8. What about this other part? About this other part, this part is similar to, oh no, we are raising, we are raising 7, which is 49. This is 7 to 2, which is 49. 49 divided by 17, no, divided by 19, 2 times, the remainder is 11. Now square this part, you get 16, 12 raised to 16. But when we squared 11 some point back, we got 7, so it's against 7. Now when you raise this one again to power 2, you will have that 2, which is beyond what we want. We just want 12 raised to 17. So it means where we've reached is the end of squaring. Now we choose from among these ones, the ones we can combine. The ones we can combine to arrive at 12 raised to 17. Earlier on, I had taught you something, and I still insist it's a good thing, especially if you have to write algorithm to do with the fast powering algorithm. If you have to do that, then you need to know that it's good to always convert this number, exponent, the power, convert it from decimal to binary. It makes your work easier. Now, so if I do that, let me just see what that would be. If we convert 17 from decimal to binary, it will give me 1 0 0 0. Those are 3 zeros, then 1. This is the binary conversion. Now, this is very important because it tells you what to combine while multiplying. It tells you, you see, this is the first, this is raised to 1. When we did raised to 1, it is this one, raised to 1. You ignore the ones that have zeros. The ones that have zeros, those ones, you ignore that. Then we have the last one. The last one, 12 raised to 16. So in fact, this one was telling us we should do it how many times? It was telling us we do it 1, 2, 3, 4, 5 times. And we did 1, 2, 3, 4, 5 times. So we did that 5 times. So if you had converted to binary, you will have known that we are going to do 5 times. And then you just begin doing the 5 times. The last one is this. And the first one is this. So it's just telling us, multiply the first and the last. So you just come here, pick the last, and then pick the first. Because that is what it's telling us. It's telling us, multiply the first and the last. So 7 times 12 is what we have here. And that gives us 8 more than 19. Because that would be 84. 84, and then you divide by 19. The remainder is 8. But look at how that binary conversion has helped us. It tells you that the only ones which I'll be combining are the ones which have ones. The ones which have ones, the first one and the last one. Although while I was doing this question, I did not consider that binary conversion, but I'm just saying in some cases, it becomes very crucial so that you know what, in fact, when you're writing algorithm, it becomes very easy if you can have that. Now let's look at the next example. I want to find the inverse of 17 mod 28. Of course, 17 and 28 are relatively prime. So since they're relatively prime, we can go straight to finding the inverse. But what does Euler say? We're just using Euler's theorem this time. Euler says that the inverse of 17 Euler phi of 28 minus 1. 28 is not a prime number, so you can get the Euler phi of 28. I remind you, we get the factors, prime factors of 28. Two goes here 14 times, 2 goes here, and then 7. The prime factors in factor 2 and 7. So that means the Euler phi of 28 will be given by 1 minus 1 out of 2 times 1 minus 1 out of 7, then times 28. 1 minus a half is just a half. 1 minus 7 is 6 out of 7, then times 28. This denominator is 14 because there are 2 times. So what you get is 12. So 5 of 28 is 5 of 28. Euler 5 of 28 is 12. But what the Euler theorem says is that we shall subtract 1 from this. When we subtract 1, we have 17 raised to 11 as the inverse. So the inverse is 17 raised to 11. Now we use the fast pairing algorithm to find out what this 17 raised to 11 is. We use that to find out what 17 raised to 11 is. I want to use the same method. First of all, convert this number 11 to binary. 11 is a decimal number. So converting it to binary, what does it become? It is 11 it will be 1011. So it's telling me that I should do how many times? It's telling me that I should square 1, 2, 3, 4 times. Then that I should square 4 times. First squaring 17 raised to 2. Let me just use my calculator. Let me find my calculator here. 17 raised to 2 is 29. Our divisor is 28. It goes there 10 times. Goes there 10 times. And the remainder is 9. That's my second. So I'm done with the second. Practice from this side. This is the first. So I've done the second. I've done the second. So beginning from this side, going this way. I've done my first, I've done my second. Let me do my third. I square 9, get 81. Divide by 28. Goes there 2 times. And the remainder is 25. So I've done the third. Let me square it. I get 625. And the divisor is 28. So dividing by 28 goes there 22 times. And the remainder is 9. This was the fourth. Now, what is it telling me? I multiply the first, the second, and the fourth. So it's telling me that I should multiply the first, the second, and the fourth. That's what it's telling me. And of course, if you want, you can start by writing this, because the first is just raised to 1. And the second is just raised to 2. And the fourth is raised to 8. So you can combine this way, so that when you come here, it'll be 17 raised to 8 times 17 raised to 2 times 17 raised to 1. But 17 raised to 8 was the fourth. And 17 raised to 2 was that one, and then that. So when you multiply this, what do you get? That's 81 times 17. 81 times 17 is 1,377. Divided by 28 goes there 49 times. And the remainder is 5. So of course, this remainder is the inverse of 17. Because that is what we're looking for. We're looking for the inverse of 17, and the inverse of 17 was 17 raised to 11. It's this 17 raised to 11 that we found to be 5. That means 5 is the inverse of 17. Now you can always confirm by multiplying this 5 by 17 and dividing by the divisor, which is 28, and see what the remainder is. If the remainder is 1, then it means it's correct. 5 is the inverse. If the remainder is 1, because the inverse of A is that number which on multiplication by A gives you 1. So what I'm saying is you can confirm by just multiplying that mod 28. And when you do that, that will be 85 divided by 28. Goes there 3 times. And the remainder is 1. So this one gives you 1. So it means 5 actually is there, is the inverse. Now it's just the same thing. It's just the same thing. I want just to do the same example so that it becomes clearer. What does Euler say about this inverse? Already these two are coprime. They're coprime. So Euler says that the inverse of 29 would be 29 raised to 5 of 75, then minus 1 mod 75. 5 of 75. So how do you find 5 of 75? 75 is not a prime number. 3 can divide it. Those digits, when you add this, you get it 12. So that means 3 can divide it because 3 can go into 12. Just a minute, let me use my calculator. Okay, so we have, so how many times? To go there 25 times. And the next one is 5, and then 5. So the prime factors are just 3 and 5. So the prime factors. That means the Euler phi of 75, therefore, is given by 1 minus 1 out of 3 times 1 minus 1 out of 5, 10 times 75. The first bracket is just 1, 2 out of 3. And the second bracket is 4 out of 5. Then times 75. This denominator here is 15. Go here 3 times. Is it 5 times? Yes, 5 times. So that you get it 20. But now, you get it 20. I think just a minute. I don't get 20. There's a 2 here. There's a 2 here. Yeah, I did not see that. I was only seeing 4 and 5. So 4 and 5 is 20, but there's a 2 here. That gives us 40. Now, but now subtract 1 because of the formula here. So it means the inverse therefore is 29 raised to 39 mod 75. That is the inverse. Now we just need now to know what is this 29 raised to 39? What is it? That's what we need to find out. That we reduce it because it's a very big number. It's bigger than 75, so you must reduce it. I want to again follow the same reasoning, the same argument, that I'll begin first of all by noting the binary. What is the power? The power is 39. So I just want to, first of all, change this 39, which is a decimal number, to binary. If there's somebody who doesn't know how to do that, maybe again we will revisit that. But we've revisited it before. So that is 39. Let's convert to, I'm just converting it. What I'm seeing is 0, 0, 1, 1, 1. Okay, there could be somebody who doesn't know how to. Let me just convert it here. 39. What I'm doing is 39. I'm dividing by 2 and then noting the remainder. I'm just using division algorithm. Let me just do that. So 39, when you divide it by 2, what you get is 19, and the remainder is 1. Then 2 here. So we're changing from decimal to binary. So that means we divide by 2. Binary is base 2. That's why I'm getting the 2 I'm dividing with. Base 2. Binary is base 2. So I divide by 2 throughout. Note the remainder at every stage. 2 into 19, go there how many times? You go there 9 times. And the remainder is 1. What about 2 into 9? Goes there 4 times. The remainder is 1. What about 2 into 4? Goes there twice. The remainder is 0. 2 into 2 goes there once. The remainder is 0. Then 2 into 1 goes there 0 times. What is the remainder? The remainder is 1. So we've reached the end of that. The only thing I did is that I wrote something where this 2 is I was supposed to write it here. And this one I was supposed to write it here. Okay, then after that, you note the remainders from the bottom going up. Note the remainders from the bottom going up. The first remainder is 1, is 1, then 2 zeros, then 3 1s. That's how we convert from decimal to binary. I know that there could be some who joined us along the way and we had already done this. So I thought I should show that. So we've converted from decimal to binary. And I've just said this one is not very necessary, but very important. It actually tells you what you will multiply at the end and how many times you're squaring, so that if you are informing your program how many times it should go, the program will know how many times it's going. If it's depending on this binary, you'll know I'll do this, I'll do this. And after that, which one am I combining? The ones which have ones are the ones I'm combining. Okay, so we've converted that to binary. Let's now proceed. I'll do again another example. If there's somebody who has not understood how to convert from decimal to binary, the next example again, I'll show that. So converted from. So what is it telling us? That we will square how many times? 1, 2, 3, 4, 5, 6 times. We're going to square 6 times. The first one is here. 29 raised to 1 is just 29. Then you square this line to get the next line. That will be 29 square. What about 29 times 29 on the right-hand side? Now 29 times 29 is 841. Divided by 75 goes there 11 times. And what is the remainder? 16. I'm just using my calculator, so you just use yours so that we move together. Now let's square this side, this line to get the next one. The left side is okay to be 29 raised to 4. Let's square 16. Get 256. Now divide by 75. Goes there 3 times. The remainder is 31. How many times have we done? We've done the first one. And the first one is this one. This is the first one. The one I'm ticking. And then the second one is this. We've done the third one. And it's this one. We are beginning from this side, going this way. Let's do square this third line to get the fourth line. 31 times 31 will be 961. Just moving slow so that you also use your calculator, that you see how we were doing it. 961 divided by the divisor, which is 75, goes there 12 times. Goes there 12 times. The remainder is 61. Let's square that together. Next one. This will be 29 raised to 16. 61 square is 3,721 divided by 75. Was there 49 times? Was there 49 times? The remainder is 46. Now square that 46. You get 2,116 divided by 75. Goes that 28 times. The remainder is 16. How many times are we going to do? We're going to do 1, 2, 3, 4, 5, 6 times. How many have we done? 1, 2, 3, 4, 5, 6 times. We've reached the end. Now I want to use this binary again to tell us which one we're going to combine. It's telling us combine the first one, the second, the third, and the last. So it's just telling us that 29 raised to 49 is the same as 29 raised to the last is 32. The third last On the third is 4. And then this is the second, which is 2. And then the first, which is 1. And that means, of course, when you add these powers, they should total to 49. This means that we have the last, which is 16. And then this third, which is 31. Then the second, which is 16. Then the first, which is 29. When you use your calculator, this is what you get, 44. This is what you get. Now let's look at the next example. And again, I'll be converting somewhere to binary so that our friends who joined us along the way can also get to know what we are doing. Before we convert, we must know what it tells us about the inverse of this. Of course, this number 83 is bigger than 75, no, than 17. 83 is bigger than 17. So what it means, we should first of all reduce 83, mod 17 to find the remainder. So you get the divide 17 into 83 first of all. When you do that, 17 goes there 4 times, and the remainder is 15. So 17 goes into 83, the remainder is 15. So what that means, therefore, is that 83, the inverse of 83 is just the same as the inverse of 15, mod 17. That's what it means. The inverse of 83 is just the same as the inverse of 17. Okay. Now, so, and what is that according to Euler? According to Euler, what is this? This is the same as 15 raised to 5 of 17. Euler 5 of 17 minus 1. 17 is a prime number. The Euler phi of a prime number, as we said, is just that prime number minus 1. In this case, it is 17 minus 1, which is 16, then minus 1 again. This 1, you get 15 raised to 15. Mod 17. Now, when we reach there, we use our first powering algorithm to find out what is 15 raised to 15. And it's at this point I've said, I'll show how to change this 15, this power 15 from decimal to binary. So what is it? Let me just open my calculator. We begin by division. How many times 2 goes there? 2 goes there 7 times because of 14. And the remainder will be 1. 2 goes here 3 times because of 6. And the remainder will be 1. 2 goes here once, and the remainder will be 1. We do it until we have a 0. So 2 goes here 0 times, and the remainder will be 1. So that means this number 15 to binary, we note these remainders from bottom going up is 1, 1, 1, 1, 4 ones. It's telling us that we will square 4 times, then combine all of them. It's telling us we do 4 times. The first time is 15 raised to 1, which is 15. What about the 225? Okay, 15. Can you hear me?
Yes.
Yes.
Just a minute. Now 15 square is just 225. Now divide that by our divisor, which is 17, goes at 13 times. Goes at 13 times, the remainder is 4. Now square this, get the next line is 15 square, 15 raised to 4. And then when you square this, you get 16. You see, this thing is very easy, just squaring the previous. So if you're writing a program, maybe just tell it, squaring the previous, so to get the next. And then when you square this line, you get this 15 raised to 8. So what about 16 square? 16 times 16 is 256. Divided by 17, goes there 15 times. The remainder is 1. We were to do 4 times, and we've done the 4 times. Done the 4 times. Now we've reached at a point where we must now square. We must get where we should get 15 raised to 15. Go back to our binary number. It's telling us we combine all of them because all of them have ones. So what it's telling us is that 15 raised to 15, just 15 raised to 8, plus 4, plus 2, plus 1, which is 1 times 16 times 4 times 15. I didn't write the answer here. Just do it. Now, so it's mod, in fact, this is easy. Also, it's mod what? It's mod 17. All these numbers are very close to 17. Like this one, I can see it's close to 17. So it's, then instead of this, I can write -1 here. In fact, I can say this is same as 1 times -1 times 4 times -2, which is what? 8. It is 8. Because negative times negative will be positive. 4 times 2 will be 8. That is the answer. Otherwise, if you want, you can multiply 16 times 4 the way they appear there. 10 times 15, you get 960. Then divide by 17. 17 goes there 56 times. 56 times and the remainder is 8. You still get the same answer, but I've tried to simplify. I use smaller numbers. Now let's do this. I want to do this. This again is a bigger number than 119. As we've done before, we begin by reducing it. So I divide 353 by 119. It goes there 2 times. And what is the remainder? The remainder is 115. So what this therefore means is that if you're given 353 inverse, this is just the same as 115 inverse mod 119. Because 353 is the same as 115 mod 119. But what is this according to Euler? It will be 115 raised to Euler phi of 119 minus 1. 119 is not a prime number. So we get to find out what are the factors of 119. 1 plus 1 is 2. Which number can go there actually? Which number can go into 119? Try it. Because that is how now what I'll be doing tomorrow. I'll be showing you how to factor a number without taking long time thinking about what could be the factors. But you see, before you look at any algorithm, you always try the smaller numbers. You try the smaller numbers, you try 2, you try 3, you try the smaller prime numbers and see which one could be a factor. You try the smaller numbers first. Once they fail, then instead of wasting a lot of time, you look at an algorithm that we'll be looking at. We shall be looking at algorithms tomorrow. We may not look at all of them, but just a few. Now, so you try the smaller numbers. You try 2 cannot divide this number. 3 cannot because the sum of these digits is, I'm trying the prime numbers. I've tried it, 2 has failed. 3 has failed because the sum of these digits is 11. And 3 cannot divide 11. 5 is the next prime number. Again, it cannot, here should be 5. 7 can divide this now. 7 divides, 10 divides this. So the prime factors, therefore, so you try this, so you use trial for the smaller numbers. But once you reach a level where you think that trial is now taking a longer time, you see, trial will always take a very long time, especially if the number was very huge. If the number was very huge, it would take a long time using trial. But algorithms come in now to make, they can also take a bit longer, but not as long as trial. But faster than others. So we'll be looking at them. Now, so what is phi of, Euler phi of 119 Euler 5, 119 is 1 minus 1 out of 7, multiplied by 1 minus 1 out of 17, then multiplied by 1. So the Euler 5, 1. You lost me.
Yes, at Euler 5, 119.
After this formula, I got lost before doing this. So
no, right
it
there.
is
Euler 5. Yes.
okay. So this is 96. 1 out of 6, no, 6 out of 7, then 6 out of 17 times 119. The numerator, the denominator and the numerator here, they are equal because 7 times 17 is just 119. So what I'm left with is 96. 96 minus 1, according to this formula, it is the Euler 5 now 119 minus 1, which is 96 minus 1, gives us 95. 96 minus 1 gives us 95. So the power is 95. So what therefore that means to us is that the inverse of 115 is just 115 raised to 95 mod 119. It is this 95 that we agreed that it's easier we change it to binary. And how do we do that? We ask ourselves, 2 there how many times? What is the remainder? 2 into 9 is 4. Remain 1 into 15, 7, and then the remainder is 1. 2 into 47 would be 2, 3, and the remainder is 1. 2 here would be 1, 1, the remainder is 1. 2 here would be 5, the remainder is 1. 2 here would be 2, the remainder is 1. 2 here would be 1, the remainder is 0. And the 2 into 1, we do it until we get 0. The remainder is 1. So we note from the bottom, this is 101, 101. Then how many ones? 4 ones. 1, 2, 3, 4. So it's in fact telling us that we're going to do 1, 2, 3, 4, 5, 6, 7 squares. We're going to do 7 squares. This is what it's telling us. So let's do the 7 squares. with our calculator. The first one does not require our calculator. Is 115 raised to 1, which is just 115. I'm preparing my calculator for the second one. So 115, we found this 115. Let's now square it to get the next one. 115 times 115 is 225. Our divisor is 119. It goes there 111 times. 111 times. The remainder is 16. That's what we write. Square this to get the next one. 16 times 16 is 256. Divided by 119, goes there 2 times. And the remainder is 18. Square that to get the next one. Square that to get the next one. So 18 square is 324 divided by our divisor, which is 119, goes there 2 times. The remainder is 86. Square 86 to get the next one. 86 square, just a minute, where is mine? Let me write again. 86 square is 7,396 divided by 119. Goes there 2 times. The remainder is 18. Get 324 divided by 119. Goes there 2 times. The remainder is 86. So far, how many times have we gone? We were supposed to go 1, 2, 3, 4, 5, 6, 7 times. We've gone to, so we square 86 and get 7,396 divided by 119. Goes there 62 times, and the remainder is 18. Good. Go back to what is telling us to combine. Telling us combine all of them except second last. Except the second last. Combine all of them except the second last. So this is the only one will not be considering. So this is the only one we will not be considering. The rest are considered according to this binary number. So that means 15 raised to 95 is the same as 15 raised to 64 plus 16 plus 8 plus 4 plus 2, then plus 1. Mod 119. But what is 115 raised to 64? Is 18. Raised to 16 is another 18. Raised to 8 is 86. Raised to 4 is 18. Raised to 2 is 16. Then raised to 1 is 115. Let us see whether our calculator can handle all of them. If it cannot, then we will pair them. Let's try to use our calculator and see. I have 18 times another 18 times 86 times 18 times 16 times 115. Yes, it can handle. Because I can say I have 18, 18, 86, 18, 16. And what I'm getting, therefore, is a huge number, 922,855,680. This is not important. What is important is that I should divide by 119. And it has gone there a number of times. It has gone there 77, 55, 089. And again, this is not very important. What is important is the remainder. So what is the remainder? Let me find out the remainder. I've noted that number of times. It was 77, 55, 089, and the remainder is 89. The remainder is 89. Let me go to the last example. There's no question in the chat. Last example is here. Bigger than the divisor. The number given to us is bigger than the divisor. So we reduce it. 1787 divided by 215 goes there 8 times. What is the remainder? 67. The remainder is 67. So what that means, 1787 inverse is the same as 67 inverse mod 215. Yes. Now what is that according to Euler? According to Euler, this is inverse is given by 67 raised to 5 of Euler 5 of 215 minus 1 mod 215. But what is 5 of 215? What is it? 215. This one is easy because you can see 5 can divide it. 4 times here, 41. Is there another number that can divide this apart from 5? Any number that can divide 49? 41. anything that is known apart from 41 itself? Is it 41 or 43? It's 43. It went 4 times because of 20 and remained 1 into 15 3 times. So it's 43. So that the factors, the prime factors are just 5 and 43. So that the Euler phi of 215, therefore, is 1 minus a fifth multiplied by 1 minus 1 out of 43, then multiplied by 215. But this first one is just 4 out of 5. And this one is 42 out of 43, then times 215. 5 times 43 is just 215. And this is 168. The numerator is 168. 168 minus 1, you get 167. This time, I not convert it to binary, but I've already converted that, the steps, because you now know them. We are going to find 67 raised to 167. 67 once is that you square this and divide by 215. The remainder will be that when you use your calculator. And then you square this and divide by 215. The remainder will be 31. Now square 31 divided by 215. The remainder is 101. Square 101 divided by 215. The remainder is 96. Square 96 divided by 215. The remainder is 186. And these are the number of times you're going to go. We're going to go this number of times. 1, 2, 3, 4, 5, 6, 7, 8 times. So when you square this, divided by 215, the remainder will be that. And then finally square this, divided by 215, the remainder is that. It's telling us combine the first, the second, the third, then skip 2 and combine with that, and then skip 1, combine the last. So the first 3, 67, 189, 31. 67, 189, 31. Then skip 2. Skip this 2. Skip this 2. Then the next one, 186. Then skip 1. The one that has a 0 there, skip it. Then note the last one, which is 146. You can multiply all of them and divide it by 215. This is what we get as the inverse of 17. If you discover that on squaring, on multiplying this, they're huge than what your calculator can accommodate, square these 2 first, then divide by 215, not the remainder. That remainder multiplied by 31. Then the result divided by 215, not the remainder. That second remainder multiplied by 189 and continue that way until you get 138. Thank you.
Thank you. Let's meet tomorrow for continuation, then Thursday for more practice. So have a good night.